Hello everybody. What we're going to be looking at today is applied optimization. So good news and bad news about this. So the good news is that it doesn't require you to learn any more math than you already know. The bad news is that these problems are, pretty challenging really. We'll learn how to do a bunch of them and, you'll take that with you to other classes. So they expect you to know the basics of this when you go to future calculus classes. Okay, let's go ahead and get into it then. So first of all, what is optimization? So optimization is when you are trying to find the values that will make a function do what you want. So typically a minimum or a maximum is what you're looking for. So optimization. That's going to be figuring out the parameters or the values for the variables in a function that will either maximize or minimize the function. Why can't I write words? Minimize the function. All right. So you can take entire classes in optimization. So if you're a math major or a computer science major, as a junior or a senior, you can take a class in applied optimization or optimization techniques or anything like that. You can do it in graduate school. It's an important thing, right? So it's just figuring out how you're going to get the function to be a maximum or a minimum. That's it. And so, of course, you can see that this is something that you already know about because you know about finding maximums and minimums already. We already know, I'll write that, we already know how to find either absolute minimums and maximums, absolute extrema, and local extrema. And that's it, right? So we're done. So what is this section even if we already know how to do it? Well, what we don't know how to do is we don't know how to go about solving word problems that you have to do. And so mostly what this section is about is not any new kind of math. It's just learning about some specific word problems and how to set them up and how to solve them. That's what it's about. Okay, just getting used to the process because these are typically pretty long problems. So you want to be very methodical is what it comes down to. All right, so could we have steps here? Maybe we have a procedure to follow. So I'll say procedure for solving applied optimization problems. All right, so the first thing you're going to want to do is draw a picture of what's going on. Just like you would for like related rates or something. You want to draw a picture, if possible, of the situation. All right. Then what you want to do is you want to write an equation for whatever you're trying to minimize or maximize. So write an equation for the quantity you want to optimize. Quantity you want to minimize or maximize. For us, we don't care. In fact, if you take a class in optimization, what you'll do is actually they only teach you how to find minimums of functions pretty much. And then if you ever want to find the maximum of a function, then you just take your function and you put a minus sign in front of it. And now it's upside down. So you find a minimum of that, and it's actually finding the maximum of what you wanted to maximize. But minimum, maximum, same difference, right? You do it the same way. So write an equation for the quantity you want to minimize or maximize. Now, what often happens is that the equation that you write has more than one variable, and that's a problem because you can only take the derivative with respect to one variable. So like if you had f as a function of x, y, and z, you're in trouble because you can't take the derivative with respect to x and y and z. You do have techniques for how to do it in Calculus 3, but we're not in Calculus 3, we're in Calculus 1, so we can't do that. So you write an equation for the quantity you want to maximize or minimize. You've done that. Now, if your equation has more than one variable, I'll say independent variable. So like, let's say you're maximizing the volume, right? And you have volume is x, y, and z. Then x, y, and z are the independent variables. They can be anything. So if you have more than one of those, then you need to use some kind of constraint in the problem. A constraint is like another equation that restricts your variables in some way. Use some constraint to eliminate those variables and get it down to one. So to get it down to one variable. You don't always have to do that, but sometimes you do. Now, once you've done that, then you should have an equation that you want to minimize or maximize. So what you're going to be doing is you're going to be find the typically absolute maximum or minimum of your function. And that's it. You're done. Okay? So, I mean, really, you can think about this as a lot of text here, but really all I'm saying is, write down the equation that you're trying to maximize or minimize and then find the maximum or minimum. So, keep that in mind that it's not conceptually difficult. You already know how to do it. Now let's go ahead and look at some specific examples here. So here's a typical example, I'll say. So it's a word problem. They're all word problems. That's where it's hard. So the thing to keep in mind about word problems is every word problem is really hard the first time you solve it. The idea is you solve the problem once, and then you're going to remember how to solve it the next time you see the same problem, right? You're not going to remember the answer. You're going to remember what the steps were to solve it. And that's what we're going to do here. So let's see. A 27-inch by 72-inch piece of cardboard is used to make an open-topped box. And this is the sort of thing that you get used to. Like when I say used to make an open-top box, you're like, what? How are you going to do that? And then I'll describe it, and you're still going to say, well, how are you going to do that? So 27 by 72 piece of cardboard is used to make an open-topped box by removing a square from each corner I'll write that nicer, corner of the cardboard and folding the flaps on each side up. Okay. Now, the question is, what size square should be cut? Squares, they're all the same, but what size squares should be cut out to make a box with maximum volume. All right. Now, again, remember what I said. I said the first time you read this, it doesn't make sense. But I'm going to show it to you, then it will make sense. So after it makes sense, you will just remember how we did it. So then next time you have to do it, you'll be able to. So here, here's your 27 by 72 inch piece of cardboard, right? So what you do is you cut out the corners. So I will, really? So I'm not going to draw this exactly like the same shape. Hey. Come on, just draw the stupid line. Just draw the line. Didn't want to draw the line. All right, so the idea is that there were corners here that we cut out. So like, we cut out that corner, cut out that corner, cut out that corner, we cut out that corner, right? And then you fold the flaps up. Now what are the flaps, right? The flaps are this. That's a flap, that's a flap, that's a flap, that's a flap. So you fold those sides up, and then you get a box like that, right? And the top is going to be open, because if you fold up the sides, there's not going to be a top to the box, but there'll be a bottom to the box. Right? Does that make sense? So that's how you make a box. Okay, and so that's what's going on. And so once you've done the problem one time, now anytime somebody says, oh, you take a flat piece of cardboard and you cut the corners out and then you make a box, you just go, oh yeah, I know exactly what you're talking about. I've seen that before. So all right, how do you do it? So the idea is we need what do we do? Well, we drew a picture, so we did that. We need to write an equation for the quantity we want to minimize or maximize. So we need the volume of the box, right? But specifically what we need is we need to know the dimensions of the box in order to come up with the volume, right? So we want to come up with an equation here. So I know equation. I don't know why I put it in a circle like that. We know that the volume of a box, right, is simply length times width times height, right? But we need everything in terms of one single variable. So we got to figure this out, okay? So here's how you're going to do it. You've got, like on this picture here, this distance. How far is that distance? It's like 72, right? Just comparing it to the other picture, that's 72. Now, how big are the squares we're cutting out, right? We have to figure that out, right? It says they're asking what size squares should be cut out to make a box with maximum volume. So what you do is you need to label the corners that you're going to cut out. So like let's say that this distance is x and this distance is x. So this distance is x, and this one's 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 x. Right? Those are all x. Okay? So then, if you think about it, what is this distance? What's this distance then? Right? The whole thing from here to here is 72. But the flap is not 72. The flap is not 72 because we cut out x. But we cut out x on the left and we cut out x on the right. So the pink here is actually going to be the 72 minus, excuse me, what is that? 72 minus 2x, because we cut out x on the left and we cut out x on the right, so we get 72 minus 2x. And you got to do the same thing for the other side. So the side started out 27, right? Started out 27. So with that said, what is this distance going to be? Well, it's 27, but then we cut out x and we cut off x. So 27 minus 2x. Right? So when you get here, you have one side is 27 minus 2x. The other side is 72 minus 2x. And how tall is the box? How tall is the box? Think about it. If we take this flap, right, and we fold it up right there at this red dashed line, how tall is the box going to be? Isn't it just going to be x? It is, right? So the volume of the box is going to be the length times the width times the height, which is just going to be 27 minus 2x, 72 minus 2x by x. So you have to do all that work. And again, it's hard the first time, but then you're going to remember it later. So my volume equation is length times width times height. So 72 minus 2x, 27 minus 2x by x. That's my volume. So that's what we were trying to do there. Okay? Now, what's next? Write the equation for the quantity. If your equation has more than one independent variable, use some constraint to get it down to 1. Okay, we just did that. We got it down to one variable. Now find the absolute minimum or maximum, right? So that's all we have to do. Once we have the equation, that was the hard part. Now we just want to find max volume. Now technically we are not trying to find the max volume. We're actually trying to find the x value that gives us the max volume. Because they didn't say what is the max volume, they said what size square should we cut out. But you know, if you know the answer to one of those, you know the answer to the other one. So find the max volume. All right. So what we really are trying to do here is we are trying to find the absolute maximum of V, right? And if you have a closed domain, then you can write the closed domain. If you don't have a closed domain, don't worry about it. But remember how we did absolute extrema on a closed domain a few sections ago? You could do that here. It doesn't matter if you do really though. All you would do, you'd say find the absolute maximum of V for x in, and what you would put here is just if you happen to know what the minimum and maximum x values are, you'd put them in here. So like for example, x is the size of the square that you cut out. So what's the smallest possible square you cut out? The smallest would be if you just cut out nothing, right? So smallest would be x equals 0. Now that's not a very good box, but that's not important. So we could cut out nothing. That's one thing we could do. Now the maximum x value you could put in would be, well, think about it. If this, like the bigger the x is, right? The bigger the x is, the smaller, like the smaller the sides get, right? Like when x is big, this gets small. The bigger the x is. And so actually the smallest, or the largest x could possibly be is like, what if x was 13? Or like, well, 13.5. If x was 13.5, 27 minus 2x would be 0. Right? If x was 13.5, it'd be 27 minus 2 times 13.5, and that would be 0. And then there'd be no side left, and so you couldn't go bigger than that. So if you happen to know that, you could write that down. If you don't know that, don't worry about it, okay? But if you do, write it down, okay? And that's what we're trying to do. We're trying to find the absolute maximum. So let's try to do it. So my function v is, we have it here, 72 minus 2x, 27 minus 2x, x. All right. Now, I can't do calculus on it this way. I need to multiply this all out. So that's what we have to do. So I grab a calculator. I'm going to FOIL this out. So 72 times 27. That's 1944. Then I have minus, it looks 54x. And then I have minus 144x, I think. 72 plus 72. Wait, no, 72 times 2. Yeah. Okay, 144. Is that right? Yeah, that's right. Sorry. And then plus 4x squared for the last term. And all of that is still multiplied by x. So I get 194 minus 54 and 144 is 198 x plus 4x squared times x. So I'm going to write it in descending order, so the opposite order that it's written there. So 4x cubed minus 198x squared plus 194. Wait, that's 1944, right? Why did I put 194? 1944, x. Okay, so that should be right. So that's my volume. Now, that's just finding the volume. Now we need to actually find maximum, right? Look for max. How do we do it? Right, we need critical points. Critical points. So you're going to take a derivative, right? You know how to do this. V prime is going to be the derivative of volume. So it's going to be 12x squared minus, what's 198 times 2? 396? 396? 396. 396x plus 1944. Okay, so I took the derivative. We're going to set it equal to 0. 0 equals 12x squared minus 396 plus 1944. 396 over 12. Does 12 go into that? Yeah. Does 12 go into 1944? Yeah. Okay. So I'm trying to solve this. I'm gonna factor out of 12. If I factor out of 12, I get x squared minus 396 over 12 is 33. That should be x. 33x. 1944 over 12 is 162. So I get this. We gotta try to factor this. Does it factor? What do you think? Just checking real quick here if it does factor. So I'm looking for numbers that multiply to 33 that add up to, multiply to 162 that add up to negative 33. I don't know. Let's just go to a computer, right? Well, actually, I'm going to use, I was going to use my calculator, but I don't want to, so I'm not. Wolfram. While I'm doing that, x squared minus 33x plus 162. X squared minus 33x plus 162 equals 0. Is that right? Minus, plus, minus, plus. 6 and 27. Wait. Oh yeah, okay. It does factor. 6 times 27 is 162 minus 6 minus 27 is negative 33. All right, so 6 and 27, huh? 6 and 27. So this is 0 equals 12, x minus 6, x minus 27. Why didn't we just do that in our heads? All right, so it did factor, but I just did it on a computer because I'm lazy. And I get x equals 6 and x equals 27. All right. Now, something that you can see right away is that 27 is not going to be the answer, right? Couldn't possibly be the answer because x equals 27, you can't cut 27 inches out of the corner of a side that's 27, right? So that can't be the answer. And that's the only reason why you want this kind of thing, because you know that 27 can't be an answer, but that's fine. So we can throw this out. If you notice, you throw this out. Throw out. You can't cut 27 inches out of a 27-inch side twice, right? Because you actually cut out two corners. So you can't cut out 27 inches and another 27 inches out of a side that's 27. So throw that out. So we really only have one answer. Now, if I'm being very lazy, I would type 6 into the computer right now and I would get it right, I would assume. I got it wrong. Let me see why I got it wrong. Blah, 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 blah. What was the question? Oh, no, I got it right. It said enter the area of the square, not the side of the square. Okay, so 6 is the answer here. But if I was really lazy, I would just assume that I had the answer here. The reason I would assume that if I was very lazy is because what other choices do I have? Right? Like, you know that you're looking for values that are going to find the maximum or the minimum. I guess technically x equals 6 could be a minimum, but you know, it's not. So yeah. But anyway, we found a critical point. What do you do once you have critical points? You need to somehow test them to make sure that they are maximum or minimum, just so that we know what we get. So let's do the first derivative test. Okay, so we're going to make a number line. We know this. You put x equals 6 here. This is where b prime is 0. Now, you see how I drew it? Just 6 in the middle. But if you know that, oops, not that. If you know that the smallest x could be a 0, then you put a 0 there and stop the number line because you can't have negative values. And if you happen to know that the maximum value of x is 13.5, you can put that in. But again, if you don't know it, it doesn't really hurt anything. It's just how you're drawing a number line. All right, so there's your first derivative test number line. We need to test a point in each section. So we need to evaluate v prime, so that's test points. We need to test a point in each section. So what's a point in this first section? How about 1? What's v prime of 1? So you calculate v prime of 1. Where's v prime? There's a lot of versions of v prime. I like this one. 12, 1 minus 6, 1 minus 27. What's that number? 12 times negative 5 times negative 26. 1560. And that's going to be positive, right? Because you're multiplying two negatives. So this side's positive. That side's positive. This side, what is it? Let's find out. Something in between 6 and 13.5. You just need it to be bigger than 6. What's bigger than 6? I don't know. How about 10? Anything bigger than 6. 12, 10 minus 6, 10 minus 27. So 12 times 4 times negative 17 you get negative 816, which is negative. So label that side negative. And there you go. Well, the first derivative test then says from 0 up to 6, the function goes up. And from 6 to 13.5, the function goes down. So what happens at 6? Maximum happens at 6. So at x equals 6, we have a maximum. Now, technically, the first derivative test tells you it's a local maximum. However, if you look at it, it's all the way from 0 up to 6 that the function's increasing, and all the way from 6 to 6 to 13.5 that the function's decreasing. So actually, there's only one maximum, and it's at 6. So even though we found a local maximum, it's got to be the absolute maximum, because where else would it be? Right? From 0 to 13.5, we see that there's only one maximum. So it's got to be local and absolute. So at x equals 6, we have a maximum. It's local, but also absolute. You know, don't think too hard about it, right? It's the maximum. We were looking for a maximum. We found a maximum. We're done. Okay? So there you go. Now, let's actually go back to the original problem, because you have to answer what they say. So what I said was, what size squares? That's how I worded it. Just be aware that on the homework assignment, on Newton, they asked, what is the area of the corners that you cut out? Actually, the area of each corner that you cut out. You don't add them or something. What is the area of each corner that you cut out? That's what they want. So we know that on our picture, we're cutting out x by x, right? So to actually answer the question that they ask, you would say, well, we cut a 6 by 6 inch square. So 6 times 6 is 36 inches square. And that's actually the answer that they wanted, was 36. Because of the specific question that they asked, right? So that's how these work is, you know, you could have the problem solved, but you have to make sure you answer the actual question that they asked, not some other question. Like, they didn't ask what the volume of the box was, but we could have figured it out. They didn't ask what the, how long and wide the box was. They didn't ask for the dimensions of the box. They only asked what is the area of the corner that we cut out. So 6 by 6, which is 36. Okay. So we did that. Let's do another one. I need to close this because the lag is driving me crazy. And let's open it up. Okay. So, new question. So this is another very, very common question, okay? Another very common question. So, let's see. Using the side of a building as one side and fencing for the other three sides. So they call this, like, this is the three-sided fence problem. So three-sided fence. So using the side of a building as one side and fencing for the other three sides, a rectangular garden will be constructed. I can't. Words are hard. A rectangular garden will be constructed. All right. there is 60 feet of fencing available. So we have 60 feet of fence. We want to determine the dimensions of the garden with maximum area and identify the max area. All right. So again, they're asking for two things here. They want the dimensions of the garden with max area and the max area. And so they actually want you to do two different things. You only type in one into Newton, but they want to make sure you know that there's different things they could ask for. What's the size of the garden and what's the area of the garden? Different things. All right, let's draw a picture. So the idea is pretty simple. Picture. So one side is a building. Okay. Now then, up against the building, you're building a rectangular fence. Okay, it won't do that because we'll make rectangles. It won't make three-sided fences. It doesn't know how. Okay, so this is what your picture is. So you've got, the red is a fence. And then the purple is building. And that's what you're building, okay? That's it. There you go. Once you have that, what are we doing next? We're trying to write an equation for the quantity we want to minimize or maximize. So what are we minimizing or maximizing? Dimensions of the garden with max area. So we need an equation for area. Equation for area. Well, we need dimensions, right? So what you have to do is you have to label the sides of this rectangle. So call them what you want. Like maybe we call this one Y and then we call this one X. Is that okay? Y and X. And then what's this one? Another Y, right? So there's your fence. What's the equation of the area? What is the area of a fence? Or the area of a rectangle? Length times width, right? So for us, I'll write it out in words and then do it. But normally area for a rectangle is length times width. So for us, A is length times width. It looks like it's going to be X, Y, right? That's it. That's the area. Now, let's move on. What's the next thing? If your equation has more than one independent variable, use some constraint to get it down to one variable. So this is the thing that we haven't had to do before. Now we have to do it. So what we have is area is X times Y. We can't have that. We need it just X or just Y. We can't have X and Y in the equation. Only one variable. So somehow get rid of that. We need to use a constraint. To eliminate one of them. Doesn't matter which one, but one of them. All right. So what is the constraint? So the constraint is a piece of extra information that we must use somehow to limit the X and the Y. And so the constraint is, well, look at the problem for a second. So look at that for a second and see if you can figure out what piece of information we haven't used yet. Right? There's something we haven't used. Side of the building is one side. Okay, we did that. Fencing for the other three sides. Okay, sure. Rectangular garden. All right. there is 60 feet of fence available. This, oops, that is your constraint. There is 60 feet of fence available. You can't make the fence as big as you want because you only have 60 feet. Okay, you only have 60 feet of fence, and that is a constraint. Okay. Oops. That's fine, actually. So the constraint is only 60 feet of fence available. Right? So that's our limitation in building this. Otherwise, there wouldn't be a maximum area, right? You know, how big is your garden? 5 million by 5 million. That's how big my garden is. Oh yeah, well I'll just build one that's 6 million by 6 million, and that'll be bigger, right? You can't though. Why can't you? Because you only have 60 feet. 60 feet of fence, okay? So when we say we have 60 feet of fence, 60 feet of fence, what's that mean? Well, look at your picture, right? Your picture is like this, and you have YYX, right? Is that how I did it? YYX? Yeah. And that's the fence, right? You have, this is not the fence, right? Only the green is the fence. So if you only have 60 feet of fence, then what you can do is you can say, well, okay, well, the Y, and the X should add up to 60, right? Because that's how much fence we have. So X fence plus Y fence must add up to 60, which is X plus 2Y equals 60. That's your constraint. Okay, that's the constraint. How are you going to get it into your equation for area? Well, all you do is you just solve for X or for Y and plug it into the area equation. So all you do is solve for X or Y, doesn't matter. After you do that, plug the result into your area equation. And that will eliminate a variable, right? So let's do that. So we have X plus 2Y equals 60. Move the 2Y over and it'll say X equals 60 minus 2Y. So we have this. And you're going to take that and you're going to plug it into area equals XY. So you're going to get area is XY, but X is 60 minus 2Y. Y. And you can multiply this out, so do so. You get 60Y minus 2Y squared. Now, the whole point of this is that it only has one variable. That was the goal of using the constraint there. Now what? Well, now we should be able to have an equation that we just maximize. So the question is, or step 4, find the absolute maximum or minimum of your function. So what we're going to do now is that. So step 4, find max min of my area equation, which is area equals 60y minus 2y squared. For y in, now again, this is the part that you don't have to do. It doesn't really matter. But how big and how small could y be? Think about it. How much fence do we have? 60. So what's the smallest y could be? Y could be 0, right? Now what's the biggest y could be? Well, you have 2y equals 60. I just I just tried to cover up something with my finger so you couldn't see it. So sorry. Can I point? Oh, that doesn't do that. This point, right? Ooh, look at that. It's fancy. So if you cover up this x, so pretend the x isn't there, it would say 2y equals 60 for your fence. So y equals 30 must be the biggest you could have, because then you'd have a 30, y would be 30, the other y would be 30, and x would be 0. All right, so that's, again, not necessary, but we did it anyway. So we need to find the maximum now. Let's do it. Back to work. Okay, so area is 60y minus 2y squared. So we're trying to maximize this, so we need critical points. Find critical points. So that means take a derivative. A prime, so y is our variable. We'll just take the derivatives with respect to y, that's fine. So the derivative of 60y is 60. The derivative of 2y squared is 4y. All right. We're going to set this equal to 0. 0 equals 60 minus 4y. So 4y equals 60, so y is 15. All right, got the y. Look at that. We got the y. So that's a critical point. Now, once you have a critical point, we need to test it, critical point, with the first derivative test, because we need to know that it's a maximum. Okay. So our number line, again, if you know it starts at 0, put that in. If you know it ends at 30, put that in. And then put your critical point, y equals 15 here. And what's special about that point? That's where v prime was 0. Okay, now we need to do test points. We know how to do that too. Test points. One from each section. Where's y prime, or a prime, by the way? I need to look at it. Where is it? A prime is 60 minus 4y. Okay, 60 minus 4y. So we need a prime of something over here. What's in between 0 and 15? Anything, right? How about 2? So a prime of 2 is 60 minus 4 times 2. That's 60 minus 8, so it's 52. So that's positive. Then you need a prime of something in the other section. So something over here. So something between 15 and 30. Now, if you didn't have the 30 there, you would just say something bigger than 15. And that would be fine. So what's bigger than 15? I don't know, 20? 20 is bigger than 15. So 60 minus 4 times 20. So that's 60 minus 80, that's negative 20. So that's negative. So that means that the function goes up, and then the function goes down again. So we verified that A has a max at y equals 15. All right? Okay, great. Now, really, we're done with the problem, but we need to answer the specific questions that they asked, right? So we need to look back at the problem statement and answer the questions that they ask. All right, now here's what I know, right? We already know y equals 15, I guess feet, right? We were measuring in feet. Y equals 15 feet gives max area. I know that. Okay, I'm just writing it down. Now, what are we actually asked? We are asked, determine the dimensions of the garden. So here's a picture, right? Garden in the middle. So we already know y. What are we missing? We're missing the x, right? So we're missing the x. So we have y, we need x. So we need the dimensions. We need to know x as well. All right, we need to know x as well. How do we do that? Well, there must be an equation that relates x and y. Look for the equation that relates x and y. And there is one. There is one because that's what the constraint did. So look for your constraint. Where's the constraint? Here it is. Right? Your constraint is, well, right here, but also right here. X is 60 minus 2y. Right? So you just kind of look back into your problem and you'll see that you have an equation that will tell you how to calculate the x from the y. X is 60 minus 2y. Constraint says x is 60 minus 2y. So x is 60 minus 2y, but y is 15, right? So 60 minus 30, which is 30. So this is what we did. That's how we calculate it. So now back here, y equals 15 feet gives max area. That's x equals 30 feet. So x is 30, y is 15. That's what gives max area. Now the other thing that they asked was, what is the max area? So last thing, what is max area? Well, you have an equation for that, right? What was the area? What's the area? Area is just right here, x times y. So go back here, area is x times y, which is 15 times 30 is whatever it is. 15 times 30, 450 square feet. So what you got is, here are your dimensions that give you the max area, and your max area is 450 square feet. Because that's what they wanted. So you're just interpreting what you can get from that y equals 15 that you had. All right, and that's the three-sided fence problem. Now something you might notice is that it came up 15 by 30, right? One of the dimensions is exactly double the other one. That always happens. In the three-sided fence problem, it's always one of them is double the other one. So like you could actually cheat once you know that problem. All right, so let's see here. There's another open top box. Awesome. There's another three-sided fence. Awesome. What else is there? There is a open-topped box. Not a lot of variety, I'll say. Okay, here, this is what I wanted. There's one other problem type on here that's, it's the most confusing to me, and that's why I saved it for last. So hopefully we're awesome at these now. All right, example. Okay, so first of all, they give us a picture. I'm going to draw the picture first, and then maybe we'll make sense of it as we go. They draw a dot and a line. They draw another dot. This says 10 miles. This dot is labeled cottage. Cottage cheese. Do you like cottage cheese? I feel like I do right up until I buy it and then try to eat it, and then I don't anymore. This is 7 miles. This is an island. How is that an island? Well, they have a dashed line here, and it says shoreline. All right, so the idea is this is out in the water. Okay, and then the cottage must be on the shore. Okay, so this is the picture they have. They don't have the blue lines, but they have the other stuff. Okay, so the 10, the 7, the cottage, the island, and the shoreline. All right, what's the text say? The text says, whoa. A visitor is staying in a cottage 10 miles east of the closest point on a shoreline to an island. All right, that's what they're describing here, right? Like if I get rid of this blue here. So what they're describing is the cottage is 10 miles east, right? So this is 10 miles east. This point is the closest point to the island, right? Because it's like a 90-degree angle right here. So that's the closest point to that island is this purple dot. Oh no. This purple dot is the closest point to the island. Okay. Great. Now what's that? What are we doing with that? Okay. The visitor is going to travel to the island by running and swimming. Okay. So, the visitor runs at 5 miles per hour and swims at 3 miles per hour. How far should the visitor run to minimize the time it takes to reach the island? All right. Now, again, this is confusing, but it'll make sense when we look at the picture here, right? So remember, everything below the cottage is water, right? So what's happening is this. So you've got your dude or whatever person at the cottage, right? So starting right here, and the person is going to travel. Let me move this. Move. Okay. We know it's 10 miles. Oh no. Why you do this? I want to... Come on. Move the 10. Stop. Delete just the blue that I just drew here that was stupid. Okay. So you've got your person, right? Here it is. Helpful drawing. They're starting at the cottage and they're going to run. So they're going to run this way some distance. Okay. Now at some point, they're going to stop running. And when they stop running, they're going to swim to the island. Like that. So first they're going to run, and then they're going to swim. Okay? So that is that's what's happening. Okay? So what you have to do is figure out how long it's going to take to get to the island. Okay, so it's going to be hard to do. So we have the picture. We need to come up with the equation. So here's how I'll come up with the equation. All right. So you do this in a series of steps. You say, first of all, how are we going to calculate the time? Right? The time. So capital T is going to be, first of all, it's going to be the time that you run. Time for running plus the time for swimming. Right? That's going to be the total time. Okay. Now, how do we calculate time? Well, you need to know the relationship between distance and time. And so the relationship between distance and time is this. So velocity, so here speed is distance over time, right? Like miles over hours is a speed. So this is not part of what we're doing. This is like things you need to know. So speed is distance over time. So stop. Why? No, stop. So time times speed is distance, or time is going to be distance divided by speed. Okay, so if we want the time for running and the time for swimming, the time for running is going to be the distance ran, right, divided by the speed of running. Does that make sense? That's how much time it'll take. Distance over speed. Now, same thing for swimming. The time for swimming is going to be the distance that you swim. Swum? No idea. That's why I am a math major. Distance swam over speed of swimming. Okay? Now, we know the speed of running and the speed of swimming because they just told us, right? So we don't have to worry about that. All we have to worry about is the distance that you run. And so we've got to look back at that picture now. Now, the picture is kind of, the more you draw on it, the more complicated it looks. But do a little simplified version of it or something. Okay, so here's my picture. So remember, this is 7. This is 10. Okay, now we have a couple of measurements here. We need to label them with some kind of variable. So remember, you're going from here to some point down here. Now, I don't know how far that distance is, right? But that's how far we're running. So let's just say x. That's the distance that we're running, right? Running distance. Right? That's the running distance. Then you're going to go to the island across the water. That's the swim distance. Okay, so we have x, which is the running distance, and then we have the swimming distance. Now, what we've got to do, though, is somehow figure out what the swimming distance is in terms of... Stop that. Move. We need to figure out what the swimming distance is in terms of the running distance. Somehow. So I called the running distance x. So already, at least, we're done with that. Seriously? Why can't I? Okay, fine. I can't move it. So x is the running distance. The swimming distance is where it is. So what I want to do first is realize that down here, there's a triangle, right? That's a triangle. And so we can relate the sides of the triangle if we know if we know two of the sides, we can calculate the third. So what we want is this. So what is this side of the triangle? So the whole distance is 10, right? And this distance is x. So how much is the blue distance? It's going to be 10 minus x, right? And being able to do that is pretty much the whole thing that you need to be able to do. Because once you realize that that's 10 minus x, now this side is 10 minus x, this side is 7, right? Let's do that. So then if you're calculating the third side of the triangle, this side, using the Pythagorean theorem, right? A squared plus b squared equals c squared, where a could be 7, b could be 10 minus x, is c squared. So it's going to be the square root of 7 squared plus 10 minus x squared. That is the swimming distance. Okay, well now we've got the whole picture labeled. We know the swimming distance and we know the running distance. So we're actually able to come down here and fill out this equation now. So the time is the distance that you run. How far did we run according to my picture? I think we ran x, right? X. How fast do we run? You can look it up. It's 5, right? We run at 5 and we swim at 3. So distance ran, x. Speed, 5. Now, distance swam. How far are we swimming? The distance swam is that hypotenuse of the triangle, which is 7 squared, which is 49. I'll write that. Minus, no, not minus, plus. 49 plus 10 minus x quantity squared. And how far or how fast do we swim? 3. How do I know it? They said so. Okay, that's my equation. So that's hard to get, but you know how to label the picture now when you see it next time. Okay, let us see if we can make some progress now. Now that we have the equation there, what we want to do is find the maximum, right? We need to find the x that will minimize the distance. So now, there's no step 3, we're on to 4. Find minimum time. T. Minimize t. Find minimum t. So we have t equals x over 5 plus, we need to work out what's in that radical there. 49 plus, and then we need to multiply this out. It's going to be 100 minus 20x plus x squared all over 3, which is x over 5 plus, what do we have? 100 plus 49 is 149. So we have, I'm going to write it this way, x squared minus 20x plus 149. That's not like a difference of squares, right? No, of course not. Okay. That's interesting. That's kind of hard, isn't it? So let's see here. Okay, I was just checking what we were doing here. All right, so that's my equation. Now what we need to do is we need to find critical points, but I'm going to write it this way. So 1/5 x plus 1/3 parentheses x squared minus 20x plus 149 to the 1/2. I just want it that way to make it easier to take the derivative. All right, now we want to look for max. So we need, our first thing is critical points. We need critical points. How do you find critical points? Take a derivative. So the derivative of 1/5 x is 1/5 plus 1/3. The derivative here needs chain rule. So you bring the 1/2 down in front, x squared minus 20x plus 149. Subtract 1 from the power, you get negative 1/2. And then the chain rule makes you multiply by the derivative of what's inside. So the derivative of what's inside, the derivative of x squared plus x squared minus 20x is going to be 2x minus 20. So this is what we get for our derivative. I can make that simpler, 1/5 plus, so fraction. On top we have 2x minus 20. On bottom I got the 3 times the 2 here, that's a 6 on bottom. And then it's a square root of x squared minus 20x plus 149. Okay, there's my derivative. Once you have a derivative, then how do you do this? Okay, so what you have to do for critical points is once you have the derivative, we want to set this equal to 0, right? So set equal to 0. So you go 0 equals 1/5 plus 2x minus 20 over 6 square root x squared minus 20x plus 149. We have to solve this. You can get a computer to help you, but I'm just going to do it by hand. So the way I would solve this is I would move the 1/5 over. Negative 1/5 equals 2x minus 20 over 6 square root x squared minus 20x plus 149. Okay, now then what I would do is, you can do this different ways. I would probably cross multiply. So you multiply these together and you multiply these together. So let me make that look a little nicer here. So what I mean by that is you multiply the 5 by the 2x minus 20, and you get 5 times 2x minus 20. And then you multiply these together. Ooh, that's hard to read. So you have negative 1 times 6 square root x squared minus 20x plus 149. So set those equal to each other. So I get 5 2x minus 20 equals negative 6 x squared minus 20x plus 149. So at least we have no fractions. I can multiply that 5 through here, get 10x minus 100, negative 6 square root x squared minus 20x plus 149. Divide both sides by negative 6. So I get 10x minus 100 over minus 6 square root x squared minus 20x plus 149. Square both sides. So you square both sides. Like that. On the right hand side, it just cancels out the square root. So you get x squared minus 20x plus 149. On the other side, negative 6 squared on bottom is 36. On top, you have 10x minus 100 squared. Is that right? Just double check. Yeah. So that's going to be 10x squared. Yeah, it's going to be 100x squared minus 2000x plus 100 times 100, which is like 10,000, right? Yeah. So that's 10x squared minus 2000x plus 10,000 all right. I'm going to bring this 36 back up to the other side, actually. So let me just rewrite this. First of all, I'm going to write the 10,000 so it's somewhat legible. And then we're going to do this. I'm going to bring that 36 up to the other side. So I'm going to have 10x squared minus 2000x plus 10,000 equals 36x squared minus 20 times 36, 720x plus 36 times 149. Awesome. 5364. Yay, calculator. This is dumb. You have to move everything to one side of the equation. So I'm going to get 0 equals, and then I'm going to subtract the entire left side from the right side. So I need to subtract 10x squared minus, no, plus 2000x minus 10,000. Hope I'm doing this right. Numbers are weird, so I feel like I made a mistake. 36x squared minus 10x squared is 26x squared. Negative 720 plus 2000 is 1200x. 5364 minus 10,000 is negative 4636. Now what I'm going to do here is stop for a second while I figure out if 26 goes into all of those things. I wish it did. Does not. Neither does 13. Okay. How did this happen? How did they get it so it was pretty looking? Just going to stop for a second to see what they did. How did they do that? Okay, they canceled that. Why did my numbers get so bad? They never multiplied that out. Okay, they kind of cheated. Okay. At this point, I'm just going to write these numbers down. 26, 1200, negative 4636. I'm just going to go to Wolfram and make Wolfram solve it to find out if we're right. And then probably just use their answer, use the answer that comes up here if it's correct. We could have just typed it in from the beginning. What's the answer? No. I made a mistake. Oh no. Okay. So we can look for the mistake. Oops. So let's look for the mistake. Let's back it up to here. Well, yeah, actually, we can just do this. So there's a mistake somewhere. So let's back it up to where we think maybe that's not a mistake. 5 2x minus 20 equals minus 6 square root x squared minus 20x plus 149. Close. Wait. Okay, that's already wrong. How could that be wrong? Okay, well, back it up. Zero equals, let's just take it to the first equation we had. 1/5 plus, we had a fraction, parentheses, 2x minus 20 divided by, and it was 6 times, and there was a square root, and I had x squared minus 20x plus 149. Close, close. So that's must be right. Okay, let's look. No, that's just what we got for the answer. Hold on. That's not the answer though, guys. Oh, it is the answer. Okay, so it was right the whole freaking time. Okay, sorry. All right. Sorry about that. Let's go back here. Let's back this up to here. And just say, if you were sufficiently motivated, you could solve this equation. It's not impossible. We asked a computer, and Wolfram says x equals, what was it, 19/4? Is that what it had? Yeah, 19/4. Okay, so 19/4 it is. That's fine. We're just going to go with that, 19/4. Now, once we have that, that's our critical point. So our critical point, that doesn't necessarily mean that we have like the final answer, right? We need to test it to make sure it's a minimum. So we should test critical point to see if it's a minimum. Well, we'll just say test critical point with first derivative test. Now, like I said before though, we could test the critical point to see if it's a minimum or a maximum, but we only have one choice here, right? Like, if this isn't the answer we're looking for, then we're in trouble because we didn't have an alternate method. So we need to test the critical point, but, you know. Now, what's x, by the way? What is x? From the picture, x was the distance that we ran, right? The running distance. So the minimum distance we could run is 0. The maximum distance we could run was 10, because if you look at the picture, right, we're 10 miles away from, well, you can see, right? 10 miles, 10 miles was from the cottage to that closest point on the shore. So that's the farthest we would run. And then we have 19/4, which if you calculate, that's 4.75. So that's like 4.75 is right there. Okay, that's your critical point. So we test 2 points, one on each side. So test points. T prime of, let's say, 1. Now, here's the thing that's sad. We have to plug that into T prime. Where's T prime? This is actually T prime, right? So that's annoying. 1/5 plus 2 times 1 minus 20 over 6 square root 1 squared minus 20 plus 149. All right. 1/5 plus 2 minus 20 is negative 18 over square root. Well, actually, the square root's got to be, it doesn't matter. It's just going to be 149 minus 20 plus 1. So 150 minus 20 is 130. So I'm just going to punch this into a calculator, but all we care about is the sign, so keep that in mind that you should be able to already tell that this is negative. I think it's negative. It is negative 0.326 dot dot dot, but negative it is. So that's on this side, negative. You need a point on the other side of 4.75. So maybe like 9 or something. So 1/5 plus 2 times 9 minus 20 over 6 square root 9 squared minus, what is it? 20x, so 20 times 9 plus 149. Okay, so 1/5 minus 18 minus 20 is negative 2 over 6. Oh, I typed that in wrong the other, by the way, on the last one. So in there it is 81 minus 180 plus 149, and that is positive 0.15. This might be wrong, but it's probably negative. I'm not recalculating it. Okay, so minus and plus. What that means is that the function went down and then the function went up. So there is a minimum. So what we know is that x equals 4.75, which is 19 over 4, is the minimum time. It's not the minimum time. It gives the minimum time. Okay, now we need to answer the question. So what was the actual question? The question was, how far should the visitor run to minimize the time it takes to reach the island? Oh, that's actually the answer, right? X was the distance ran. Visitor should run 4.75 miles, because that's what X was, the running distance. Easy. Now you could have calculated other things, like you can actually calculate how far you have to swim, right? Because you can look at your picture and the swimming distance is right here. So you know that X is 4.75, so you can calculate the swimming distance. You also know the time, because the equation for time is here, right? This is the equation for time, and you know X, so you could put in 4.75 and calculate the time in hours. But they didn't ask for that. They only asked for the distance that you run, and the distance that you run is X. So we calculated the X and we're done. The end. So that was a very long problem. They are tricky, but you know, it's mostly being able to draw like the X, the 10 minus X, and knowing that you need to find that hypotenuse of the triangle. That's the hard part. And also knowing how to calculate the time. Distance ran over speed ran plus distance swam over speed of swim, right? Using the relationship between distance and time and speed. Okay, awesome. That was very long. So that's it. Those are hard. Good luck with the homework. Come to office hours. See you later.